Welcome back, everybody. Today we're going to learn about stars and how they are born, grow old, and die, the life cycle of stars. First off, I think you should know what a star really is. These things are big, they're made of hydrogen gas, and many other elements are being created inside them, but mainly hydrogen gas and helium gas. And that gas is producing energy through the process of nuclear fusion. If we could somehow do this on Earth, we could solve all our energy problems, but stars do this quite well. And they do it for their entire lives until they die out. And what they're doing is fusing hydrogen into helium for the most part. And there's other more complicated processes that happen, and they fuse other things too. But nuclear fusion, the basics of it, shows two hydrogens fusing into one helium, and if you were to add up the masses of these two hydrogens, you would actually notice that they wouldn't equal 2m over here. M plus m is 2m. It would be a little bit less. And that loss in mass is what's converted to pure energy through the formula that we know all so well from Albert Einstein. E, or energy, equals mass, m, times the speed of light squared. And the speed of light's a really big number, and when you square it, it's really, really big. And so it doesn't take a lot of energy or a lot of mass to turn into a lot of energy. And that's why stars and nuclear fusion is so darn great. It's so efficient and so necessary for us. Now this slide you're looking at shows the path, two different paths that stars can take in their lifetimes. And I'd like to show you a different picture coming up that explains a little better. But first, let's talk about different star types. Stars can be brighter than others, they can be different colors than others, and different temperatures than others. They have different masses. And these false color images here you see of these three stars, the red, the yellow, and the blue, are there to demonstrate how different size stars and different age stars and different mass stars will have different temperatures. And as you probably already know, the color blue, in terms of light, shows the hottest of temperatures. And the color red is the coolest of temperatures. And you can see that right here. 2,500 degrees Kelvin is the temperature, and that's where stars that are red in color emit most of their light. So red stars are cool, comparatively speaking. Blue stars, like this one, they emit their blue light at a much hotter temperature, in this case 18,000 Kelvin, but it can get hotter than that or a little cooler than that. But if it's at that temperature, it's going to be in the blue color of visible light. And our sun, similar to this one here, shows its maximum colors in the yellowish, greenish, kind of orangish side around 5,800 Kelvin. And that's why our sun appears the color that it appears. And these colors are exaggerated, just so you can see them. So what you really should take away from this is that temperature determines the color of stars. And we're going to be actually examining this a little more closely with the Hertzsprung-Russell diagram, which your reference tables call something different on page 15. And they graph the star's luminosity versus its color and temperature. This is a much better color image of the Hertzsprung-Russell HR diagram. And you can see some important things here. The surface temperature in Kelvin on the x-axis, and that's measured once again in Kelvin. And the strange thing about the temperature is that it's graphed with a temperature decreasing to the right. Decreasing to the right. So the hottest temperatures on this graph are on the left side by the y-axis. You'll also see down here some letters of the alphabet. Stars can also be designated by their letters, and I always remember this by "Oh Be a Fine Girl, Kiss Me," and they line right up with that, they match up with that. O, B, A, F, G, K, and M stars. Our sun being a G-class star. You can see our sun right there, but there's many other classes of stars here. And on the y-axis, we see brightness. And the units are in solar units, which means our sun is one solar unit. One solar unit is our sun. That's how bright. We're going to base everything off the brightness of our own sun. And the axis on the numbers on the y-axis go up by factors of 10. So 1, 10, then 100, 1,000, and so on and so forth. So it increases exponentially pretty fast. All right, now you'll notice some patterns on this graph. The pattern is pretty obvious, how it shows a line of stars here, and they call that the main sequence. These are main sequence stars, and this is where stars spend most of their lives. They're in a stable state in the main sequence. And depending on how big the star was to start with, they'll stay on the main sequence for different lengths of time. The smaller stars that are on the main sequence, these ones over here, the red ones, they will live the longest. The blue stars up here on the main sequence will live the shortest. So it's like, the bigger, the hotter you are, the faster you fall. And you also notice there's stars that aren't on the main sequence. Like, for instance, the giants or the supergiants. These are stars that are in the process of dying. And whenever stars come off the main sequence and move into the giants or the supergiants stage, they're not too long for life. And you also see this other category down here, the white dwarfs. And this is where our sun will end up someday. But the white dwarfs are just, we'll learn exactly what these different types of stars are, but the white dwarfs is just another category on this chart. Now, there are a few things that aren't on this chart, which we'll get to, the exotic remnants of stellar explosions. But for now, you got the idea of the Hertzsprung-Russell diagram. Okay, this is how your reference tables represents the same thing. They just simplified the name to the characteristics of stars chart. I wish they had the Hertzsprung-Russell as the title. And it says the name in italics refers to stars represented by that symbol right here. And stages indicate the general sequence of star development. And once again, we see our main sequence right here, where most stars hang out 90% of the time. And we also see our giant stages, our supergiant stages, our white dwarf stage. Remember, these are all in the process of dying. And lots of examples are on this chart, examples that you might be asked to answer about. Our sun being the most important to us example, but you've probably maybe heard of Sirius, the brightest star in our sky, or definitely heard of Polaris. You know that from this course, the North Star. But there's plenty of others. And once again, this star is set up the same way, has colors on the bottom, and those colors correspond to hotter temperatures or cooler temperatures, or like us, somewhere in the middle. So you can compare our sun versus other stars. For instance, our sun, it's a 1, of course, in luminosity, the brightness. And if you looked at, for instance, Sirius is quite a bit brighter than our sun, more luminosity, more luminous. And I don't know if you kind of estimated there, maybe 30 or so times brighter or more luminous than our sun. Sirius is also a different color than our sun. If you go down, it's more of a whitish color, blue-white to white color, and it's hotter, around 10,000 degrees Kelvin. And that's how you read this chart. So you can do all kinds of questions with this. You can do comparisons from one to another, temperature comparisons, color comparisons, brightness or luminosity comparisons. And you can also do mass comparisons too, which they don't really show on the left-hand side, but they do on the right-hand side. Massive stars are toward the top of this graph, really big stars that are heavy, and small stars are towards the bottom of this graph. And you can see our sun is kind of slightly towards the bottom. It's not quite in the middle. That's on page 15 of your reference tables. And this chart shows how stars move when they die, or when they begin to die. So once again, our main sequence is here. Sun's here. As the sun starts to grow older, it will move to here. Now, it's not physically moving in space to there. What's happening is if you plotted the sun's brightness versus its temperature, it would end up on this graph moving. And then eventually there to there, and collapse way down to a white dwarf eventually. Bigger stars, though, they'll move into this supergiant stage eventually till they blank off right off this graph, and they'll become either neutron stars or black holes, which we'll get to later in this lesson. All right, star types. The types of stars are mainly determined by the star's original mass and how old it is at the time we're looking at it. And like I said before, 90% of most stars exist in the main sequence stage, that relatively stable state. Okay, some different types of stars. The giants, remember these ones are on their way to dying as they exhaust their hydrogen supply. And there's a picture of a red supergiant, but giants in general are red, orange, or yellow stars. They're starting to expand as they lose their gravitational grip on their gases, and they exhaust their supply of hydrogen, as I said. And the giants are located there, like Aldebaran or Pollux. The supergiants, highly luminous, massive stars. They're very bright because they're so big. It's like a giant, huge headlight. The red ones are near death, while the blue ones are living very short lives. So the red ones have lived a long life and they're getting near the end, and the blue ones don't live long at all, and they die with very explosive deaths. And there's the supergiants, the blue and the red. Blue's on the left, red supergiants on the right. The white dwarfs, like our sun will be someday, these are Earth-sized stars that have collapsed down from smaller novas, not supernovas, like our sun. And, you know, they're giving off energy. That's why they're white. So they're actually, our sun will be a little hotter when it's in the white dwarf stage, but it's just so much smaller, so it's dim. And there's the white dwarfs. Now, black dwarfs, we haven't really seen any of these because the universe isn't old enough yet, but eventually a white dwarf will cool off into a black dwarf. And this is non-luminous, so you can't really see it. That's why it's a joke there on the screen. You can't see it. And it's theoretical at this point just because we haven't observed any yet. Now, if one of those large supergiants is large enough and it begins to go into the end stages of its life and explodes in a supernova, it can collapse on itself and create either a neutron star, which is extremely dense, like a grain of sand would have the same mass as like a cruise ship or something like that, some ridiculous number, or it can become even more massive, more dense, and form a black hole, which has a gravitational attraction which is so intense that not even light can escape its grip, which is why it looks black. And we think that these are the gravitational glue for many galaxies, if not all, but many galaxies in the universe. And that is it. See you for the next lesson.